Section 10.4, calculating the geometric mean of the activity coefficients using the Debye-Huckel theory. There are two steps. We need to first calculate the ionic strength of the electrolyte solution. This is I, and then we plug in this I into this equation to compute the geometric mean ionic activity coefficients. So first, how can we calculate I? Well, first you need to know the molality of the electrolyte solute. Let's say if you have 1 mole aluminum sulfate dissolved in 1 kilogram of water, and then we say this M is 1 mole. Okay, it's 1 mole. So this is going to be just 1 mole over 2. And then you sum up all the positive ions, negative ions. Again, if you dissolve aluminum sulfate, it's easier. Put the coefficient in front of the aluminum here. I think that's 2. The charge of aluminum, that's 3. So it's going to be 2 times 3 squared plus sulfate. Over here, I think the coefficient in front of sulfate, it's 3. The charge is 2. So really, it's just 3 times 2 squared. Now you have 2 times 3 squared plus 3 times 2 squared. That's about 30. And then times 1 over 2, you get 15. So the ionic strength of 1 mole aluminum sulfate is 15 mole. Why is that? Because actually the ionic strength is proportional to the charge squared over here and to the number of ions, so that's here. Alright? Now once we have this mean ionic activity, the ionic strength, we can calculate the geometric mean ionic activity coefficients. The equation is this. You do not have to memorize the equation, but you do need to understand the relationship here. If you have, more charges, plus 3 plus 4 charges versus plus 1 charge, this term becomes more negative, and the gamma is smaller. The activity is lower. Why? Well, plus 4 charges and minus 4 charges, they attract each other. Although solvated, and the attraction lowers the chemical potential. Alright, and then also we need to put the ionic strength right in here. If you plug in this I, 15 here, and then you plug in Z plus, that's 3 for aluminum, Z minus is 2 for sulfate, you will be able to get a number here. The square root of 15 is roughly 4. 4 times 2 times 3, that's 24. So the activity coefficient is roughly e to the power of negative 24. That's a very, very small number for this 1 mole aluminum sulfate. Gamma plus minus is typically much smaller than 1 because of the attraction between the ions. And then let me give you another example. This example is easier. It's just 1 molar sodium chloride solution. Okay, this is 1 molar. How can we convert 1 molar to 1 mole? Well, we can't, but we can make approximations. In this case, I'm going to assume this 1 liter solution contains 1 kilogram of water, and then it's also 1 mole. We put 1 mole here, 1 over 2, and it's sodium chloride. So the coefficients are 1 and 1, the charges are 1 and 1. So in the end, this ionic strength is just 1 mole. We plug it in here. The positive charge, negative charge, they are all just 1. So the logarithm of gamma is negative 1.173. We solve this equation, we get gamma, the coefficient is just 0.3094. Still, this number is much greater than the activity coefficients for 1 mole aluminum sulfate, I think, which is e to the power of negative 24. That's a very, very small number. 1 over maybe 10 billion.